Okay, let's get started. Okay, so uh, actually, for the next class, we cannot have in-person lecture for the next class because uh, I have a business trip. Okay, so but I will record the lecture for the next class, and then also you can watch the recorded lecture. Okay, for the next class. Uh, so I also post the announcement on the Blackboard. Okay, so we in the previous class, so we learned about the pipelining concept. Okay, so this is very important. Okay, you need to understand. But I believe so. It's not difficult. It's not difficult to understand because so actually we are utilizing this pipelining concept in the real world. Okay, so I used the analogy of the this laundry also, but and then using the pipelining, so we can improve the performance, right? So it is because we can decrease the clock frequency, right? And then so in the performance equation, so if we reduce the clock period, then we can improve the performance, right? But we do not we did not discuss about the CPI, okay? But actually in the pipelining architecture, so we need to consider hazard. It's also very important. Okay, you need to understand the concept of hazard. Okay, so and then there are three types of hazards, and then also you can understand that the hazards are event that waste the clock cycle. Okay, so I mentioned that. So in a processor model, so we assume a processor can execute one instruction per cycle. So which means the CPI is one, but because of some reasons, the clock cycles can be wasted. Okay, and then so based on the reasons of hazard, uh, we can classify hazard into the three different types of hazard: structure hazard, data hazard, and then control hazard. Okay, so I briefly explained about the definition, the meaning of these three types of hazard. So structure hazard are caused by lack of hardware resources. Okay, and then data hazard are caused by data dependencies. Control hazards are caused by control instructions like branch or jump instructions. Okay, so but I explained that in the this pipelining architecture, we cannot observe structure hazard. So it is because we already use separated instruction and data memories, right? So actually, if we use the unified memory, so which means that if we use one memory for the instruction and data, then actually a processor needs to fetch instruction for every cycle, right? So which means that the instruction memory is occupied for every cycle, and memory instructions like load or store instructions need to access data memory. So which means that if on the current instruction is memory instruction, then we can observe a structure hazard. But in order to avoid this case, actually, we already separate the instruction memory and data memory, right? So this is the reason. And then data hazard. So actually, in a single cycle process architecture, we did not consider about the data hazard or data dependencies. Why? So it is because in a single cycle process architecture, one instruction complete each all operations within one clock, right? So within one clock, the result of instruction is stored in the register file. So written back to the register file. But in the pipelining architecture, actually, the operands, the required operands are fetched in the ID stage in the register file. So if the register operands are required, a processor reads the required operands from register file in the ID stage. But we know the result. The result of instruction is written back in the write back stage. This is the final stage of this pipelining architecture. And then what's the problem? The problem is that the following instruction, the next instruction try to read the required operands from the register file in the ID stage, but we can find that it's not possible, right? The ID stage of the very next instruction is here, but the result will be written back in this stage, the write back stage. So we can find the time gap, and then so this is the future and this is the past. So it's not possible because it's not written. It's not written to it is not found in the result. The result of a previous instruction is not found in the register file at this point. So the following instruction, the next instruction needs to wait for 2 cycles. Okay, so stop 2 cycles, so we can read this. The next instruction can read the result of previous instruction. So this is the data hazard. So we can observe that the clock cycles are wasted because the following instructions stops its execution for 2 cycles, right? So the clock cycles are wasted because of data dependencies. Okay, so this is the data hazard. So you can think that, so and then data hazard, actually this data hazard is actually very critical for the performance. So you can, so actually the CPI, if we just consider the CPI, then we can find that because of data hazard, the CPI is increased. So actually for the ideal processor, we just assume that CPI is 1, but it's not true. The CPI is larger than the 1 because of hazard. Okay. So because the CPI is increased, the performance is decreased, and we need to avoid this situation, right? And how? We can handle data hazard using data forwarding. So what is forwarding? So forwarding means that a certain information or certain data is transferred to some via some not official. So it's a free it's a transfer to earlier. Okay, so this is the forwarding. So then how can we apply data forwarding, and then why, and then I will explain why data forwarding is possible in this 5-stage pipelining architecture. So let's see this example. So the first instruction is add x1, and then the following instruction, the second instruction is serve x4, x1. So you can find that x1 is requested by this second instruction, the following instruction. So you can find the data dependency. And then for this case, so we learned that the clock cycles need to be wasted, right? But let's see when the result, this result of the first instruction is generated. So I mentioned generated, right? So, uh, so actually you can find so actually when the following instruction, this sub instruction requires X1, then this sub instruction needs to read this X1 data from register file. So this is the common case, okay? But in actually, if we just see the pipeline architecture, so we can actually the result of this add instruction is generated at this point. So so actually, so X2 and X3 are read from the register file, and then these operands are given to ALU, and then actually the result, this is the result generated at this point. So this is the later part of this clock cycle number 3, okay, at this point. So which means before writing the result to the register file, this processor already has the result of add instruction. When? At this point, right? So it's earlier than this write back stage. Okay. So what does that mean? This processor already has the result. And if we know, if we know this processor has the result already, then this result can be provided to the next instruction. Understand? So this is the data forwarding. So in this case, the result of a previous instruction is generated at this point, at this time, right? At this time, and sub instruction. Actually, sub instruction try to read X1 and X5 within this cycle in the ID stage, but actually this X1 and X5 data are required at this point. So this point represents the early part of EX stage, right? So what does that mean? So if we just check when the result is generated and then when the data are required, so we can just observe that data is generated at this point, and then the data can be consumed. Data can be required at this point. So this is the past. This is the future. If we just consider some timing, the timing of the generation of result and the consuming of this result, and this is possible, right? If we just check the timing of the result generation and then the consuming of the result. So before the result is written back in the register file, this result can be provided to the input of ALU. Right, this is possible. Okay. If we just consider the timing, then this is the possible. So actually, this is not possible because if we just check the timing, so this is the future and then this is the past, and we cannot change this order, right? But if we just check when the result, the real result is generated, and then we can observe that the real result is generated at this point, right? And then this data can be provided to the input of ALU. So in this case, so this is not official official data transfer. So it is because we just assume that so if this instruction is executed and this instruction will store the result to the X1. So this is the software concept. And then the following instruction will read the data from the X1. Okay, this is the software concept. But actually, when we implement the hardware, so we need to consider the delay, so the timing of this real hardware. But when we just check the timing of the result, when the result is generated and when the result is consumed, then we can just observe that the result is actually generated at this point, and then the following instruction can use the generated result at this point, not this point. Okay, so this is data forwarding. So in the hardware implementation, the hardware implementation can be different from the software model. Okay, it's because when I explained about the software model, I explained that the software just assume that instructions are executed atomically. So atomically means that this instruction is executed and then completed, and then the next instruction is executed and completed. So actually this is the single cycle processor model. But we already know that if we use the single cycle processor, then the performance is low. So we need to increase the performance. So we can apply pipelining architecture. But if we apply pipelining architecture, then we can observe hazard and the data hazard because of data dependency. But this data hazard can be resolved using data forwarding. Okay. So this is very important. And then actually using the data forwarding, we can avoid the many data hazard, right? So we can improve the performance. But if the formal instruction is load instruction, then we cannot avoid the waste of clock cycle. So why? Because the load instruction, this is load instruction. So when the load instruction is executed, then loading the result. The result of load instruction is generated at this point. So the late part of memory stage. And then but actually if we just use the data forwarding from the ALU, then so in order to execute this sub instruction, the sub instruction requires the data at this point, right? The early part of this clock cycle number 4. So 1, 2, 3, 4. So what's the problem? So this is the future, this is the past. So if we just consider the timing, So the result of this load instruction cannot be provided to the input of the ALU for this following instruction, the sub instruction. Right. So if we just consider the timing of data, then we can just figure out this is not possible. Okay. So this is the future and this is the past. So in this case, we need to stop this sub instruction for one cycle. Then sub instruction needs to be here. So in this case, the data, the result of this memory, the result of load instruction can be forwarded to this ALU, the input of ALU. But the sub instruction needs to wait for one cycle. Okay, so this is the load use data hazard, and then we cannot avoid this load use data hazard. So which means, so one clock cycle needs to be wasted for this case. Okay, so one cycle will be wasted. Then how can we? But so in order to improve the performance, so we need to figure out some ideas. So we need to develop some ideas that can improve the performance. So this is the compiler optimization technique. So if you see this code, so this is some code. So it could, like the A equal P plus E and then C equal P plus F. Right? So if you see this code, so then you can find that this is the load instruction, load double word. So, and then add instruction is here. So you can find the X2 and X2 here. So you can find the data dependency between load instruction and add instruction. And what's the problem? The problem is that, add instruction needs to receive data from the former load instruction, but we learned that if the former instruction is load instruction and then the very next instruction requires the data from the load instruction, then this processor needs to waste one clock cycle, right? So we can observe the pipeline stall. So if a processor needs to stop, then this is called the pipeline stall. Okay, so we can observe the pipeline stall for this add instruction. Also, we can find another load and add instruction pair. So you can find the X5 and X5. Okay, so in this code, so for this code, so we can observe 2 clock cycles are wasted. Okay, but by reordering, so by reordering the order of instructions, we can avoid this situation. So this is the compiler, so code rescheduling by compiler. So we can change the code to the like this. So you can find the load instruction and load instruction, and then another load instruction, and then add instruction. So what is changed? You can find that the code order is changed. The instruction order is changed, right? Okay, the add instruction is here, and then load instruction is here. And then you can find another instruction. But this instruction, we cannot find any data dependency between this load and then this load instruction, right? And then we can find the data dependency between this add and load instruction. But the good thing is that there is another instruction. So this instruction, this load instruction can be executed without any pipeline store, right? And then this add instruction can be executed, but actually you can find the clock cycle gap between this load and add instruction. So this add instruction does not need to stop. It can be executed because there is another instruction here. So you can find the data dependency pair from this load instruction and this add instruction. Also, you can find that another two, there are two instructions between this load and this add instruction. So this add instruction does not need to stop. Okay. So, and then you can also, if you see, compare this code and this code, then the final result is the same. Okay. So at this point, the final result is the same. So it's actually there is no problem for this code. So by changing the order of instructions, then we can avoid the load use hazard. So if we just compare the clock cycles, so this code will take 13 cycles, and then this code will take 11 cycles. Then what is the speed up? Speed up is 13 over 11. Okay, so it's around the less than 20%, but it's larger than the 10%. So you may think, oh, it's just about the 10 blah blah percent, right? So this is actually huge. Okay, in a process architecture, if the performance is improved by over 10%, then it's actually this improvement is huge. So what can you observe? Actually, we cannot avoid load use hazard, right? But by applying the compiler optimization, so compiler optimization applies the reordering of the instructions, and then using this rescheduling of instructions, we can avoid data hazard. So you may think that, oh, then we can resolve so every data hazard using a compiler optimization. But it's not true, right? So why? So in this example, the compiler optimization is possible. It is because we can find available independent instruction inside of basic block. Okay, so in the basic block, the compiler can apply the reordering of instruction, but it's not easy. It's not easy to reordering the instructions between basic blocks. So because this is the large basic block, so we can find available instructions inside of the basic block, like this load instruction, and then there's some add and store instruction. But in reality, the size of basic block is small. So I mentioned that it's around 4 and 5 on average. So it's not easy. It's not easy to find the available instructions that can be used for rescheduling, the compiler optimization. Okay. So, but if possible, then we can apply compiler optimization to avoid the data hazard. Okay, so let's learn about the control hazard. So control hazard. So I mentioned that the control hazards are caused by control instructions such as branch or jump instructions. Then why? So it is because if the branch instruction is executed, then branch instruction branch instructions change what? PC, right? Program counter. But this program counter is used in instruction fetch stage. So what's the problem? So we learned that the branch instruction, the result of a branch instruction, actually this BQ needs to use ALU in order to compare the two operands from register file, right? So which means the result of a branch instruction is reserved after EX stage. So in the instruction uses the ALU in the EX stage. But the result, the result of a branch instruction is the update of PC, the program counter. But we use, the processor uses the program counter in the instruction fetch stage. What's the problem? The following instruction needs to wait until the result of a branch instruction is reserved, but it will be reserved late. So that's the problem. So this is the, so I mentioned the next instructions needs to wait. So which means clock cycles are wasted. So this is the control hazard. Okay. Let's see why. So actually this figure shows the some optimized branch instruction, but this figure just to explain why clock cycles are wasted. So actually, so you can find the BQ here. So and then the result of BQ will be reserved at this point, but using the some optimization, so actually we can add some hardware that can compare the two results from the register file, and so we can get the result of branch instructions in the ID stage. But anyway, the clock cycles are wasted. It is because because of the branch instruction. The result of a branch instruction is used in the instruction fetch stage. So by this optimization in the ID stage, instead of the ALU, then we can get the result of a branch instruction at this point. Then this result needs to be updated to the next instruction. But actually, if next instruction needs to fetch the instruction from the instruction memory at this point. So it's not possible. It's not possible to fetch the next instruction here. So the next instruction needs to wait 1 clock for this case. But without optimization, actually the next instruction needs to wait for 3 clocks. Okay. So we can observe that when a branch instruction is executed, then the the clock cycles need to be wasted, right? So until we know the result of a branch instructions, we don't know the result of the next PC, the value of next PC. So the next instruction needs to wait. So this is also huge performance degradation. So whenever the branch instruction is executed, 1 or 3 clock cycles are wasted, right? And then this is huge performance degradation. Why? So, the branch instruction occupies the 20% of total instructions, right? And then if the one or 3 cycles are wasted, then the CPI by this branch instruction is around the 1.2 to the 1.6. Okay? So 20% or 60% performance degradation is caused by branch instruction. It's very huge, right? So how can you avoid the performance degradation by branch instruction? We can apply branch prediction. So branch prediction represent, the processor can predict the result of a branch instruction. So what is the result of a branch instruction? If we just execute the BQ, X1, X2, and target, the result of a branch instruction is the condition. The condition of this branch instruction. If the condition is true, then it jumps to the PC plus target. And then if the condition is false, then what is the PC? The PC is the PC plus 4, right? But the very next instruction will be executed. So branch prediction means that before the result of a branch instruction is reserved, then a processor can fetch the next instruction based on the predicted result. I mentioned the predicted. It's not real result, but a processor just predict. And then based on this prediction, then a processor can fetch the next instruction. So what is the benefit of this prediction? So actually, in the real world, we frequently apply a certain prediction. During the exam, so if the exam is 객관식, so there are some several numbers here, and we can just predict the answer of this question, right? So if the answer is true or false, and then we don't know the exact answer, right? But we can just select the one of this answer, like true or false, right? Even though we don't know the true the correct answer, it's no harm, right? If we just answer, just select the one of these two answers, but it's no harm, right? So we can get point or we can get 0. But if we do not predict, we will always get 0 point, right? The prediction is the same. We don't know the real value of this branch instruction, like real result of this branch instruction, but we can predict. And then if the prediction is true, it's good. Okay, the performance will not be degraded. And then if the prediction is incorrect, then performance will be degraded, but it's the same. There is no harm, okay? So we can apply the branch prediction like this. So what does it mean? So I mentioned that this is the condition and then result of the branch instruction. If the condition of a branch is true, then PC is the PC plus target. And then if the condition of a branch instruction is false, then PC is the PC plus 4. Then this is the actually normal instruction execution, right? For the normal instructions, the PC is always PC plus 4, right? So if the formal instruction is a branch instruction, but this processor does not wait for the result of a branch instruction. A processor just fetch the next instruction, assuming the branch instruction result is the false. Okay, then PC is a PC plus 4. Then what will happen? If the result of branch instruction is true, then we can just cancel the like this next instructions. And then we can fetch new instruction. If the result of a branch instruction is false, so this is the lucky case, right? Then the clock cycles are not wasted. Then the instructions can be executed as normal, right? So this is the branch prediction, the basic branch prediction in the RISC-V processor, the very simple 5-stage pipeline processor, right? So we can just assume that the result of a branch is always false, right? And then we can just fetch the next instruction. And then if this prediction is incorrect, so which means the missed. So if the prediction is so in a computer architecture field, if the prediction is correct, then it is called the prediction is hit. And then if the prediction is incorrect, then it is called the prediction is missed. So miss or hit. So if the prediction is hit, then it's good. It's a lucky case. And then if the prediction is missed, then clock cycles will be wasted. And then RISC-V, this 5-stage single pipe, this 5-stage single pipeline processor, this processor always assumes that the result of a branch instruction is false. So which means it just fetch the next instruction. And then if the branch instruction is, the result of a branch instruction is reserved in either stage or EX stage, then we can just cancel the next instructions. Okay. And then this is called the static branch prediction, just static. So static means that the predicted result is always the same, right? But what's the problem? So it is like so there are true and false questions, and then we just select only the false cases, which means the hit rate, which means that this correct rate can be low, right? If we just 찍는 거잖아요. If we just select only one answer from the true and false questions, then the hit rate can be very low. And the hit rate is low, then performance will be also degraded. Then your score will be also reduced. Then how can we select the how can you select the result? How can you predict the result of this true and false based on the history? So actually in the branch prediction, we can just apply the dynamic branch prediction. So dynamic branch prediction means that a CPU or a processor can check the history of true and false, the result of branch prediction, branch instructions, and then based on this history, the the future result of branch instructions can be predicted. So for example, this branch instruction like BQ, X1, X2, and target. So when you check this branch instruction, then the result of branch instruction is true, 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 and true. In this case, we can just predict that the next result is also true. And then if we just predict the result of a branch instruction like this, then prediction rate is also dramatically increased. So why? We can observe many cases in our code. So for example, for I equals 0, I is less than 100, and I plus plus. So this is the iterative loop. And then if this loop is jump to the start point of this loop, this means that the branch is taken, right? So taken means that the condition of branch is true, right? Because the condition is true, so it jumps to the start point of this iterative loop. And then we can just find this case. We can observe this situation very frequently in our code. So if we just predict the result of a branch instruction like this, true, 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 then it's true. The next instruction, next result will be also true. And then false, 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 false. And then the next result can be also false. So by checking the history of branch instruction, we can also increase the hit rate of this branch instruction. So by doing this, we can improve the performance. So this is the dynamic branch prediction. It's called the dynamic branch prediction. It is because a processor checks the result of branch instructions in runtime. So it dynamically checks the result of a branch instruction. Then static branch prediction is like the processor will always predict the result of a branch instruction as false. So this is the static. So the processor does not analyze the history of a branch instruction. It just statically predict the result of a branch instruction as false. So this is the static branch prediction. And then we can also apply the dynamic branch prediction. And then good news is that hit rate of this dynamic branch prediction is extremely high. It's over 95%. So we can use this dynamic branch prediction in a CPU. Okay, so by applying the branch prediction technique, we can decrease the control hazard. Okay, so hazard, as I mentioned, the hazards are critical for the performance, but we can apply several architectural techniques to reduce the hazard in the processor. Okay, and then this is actually very important. Okay, so pipelining summary. So using the pipelining, we can improve the performance of processor. So by reducing the critical path delay in a processor, then we can increase the clock frequency of a processor. And then actually this pipelining architecture, the pipelining, many instructions are being executed. So for example, if you see the this figure, you can find that during this clock cycle, you can find three instructions are being executed. And then also the latency of a single instruction is the same or can be increased, right? So actually pipelining, if we just focus on the single instruction, the latency is not decreased. The latency is the same or can be increased. But if we just apply the pipelining design, then we can increase the amount of instructions, the number of instructions per unit time. That means we can increase the throughput, okay? So if we just consider the number of instructions, then the pipelining architecture can increase the throughput because the multiple instructions are being executed in parallel by different stages. And then also you need to understand the hazard. And I mentioned that this is very important, okay, very critical. So, and then there are three types of hazard, okay? So this is the basic of the pipelining. And then we will learn how to implement the pipelining architecture in the hardware. Okay. So in the previous classes, we learned how to implement the single cycle processor, right? And then now we will learn how to implement the pipeline architecture. So we can start from the single cycle processor architecture, right? So this is the hardware architecture of the single cycle processor, right? And then we can just split the operations by this single cycle processor into 5 operations. 5 operations are, so this is also important, instruction fetch, instruction decoding, execution, and memory write back. And then we can split the operations in the single cycle processor. So this is the instruction fetch. So instruction fetch, we just update the PC, and then we using the PC, then we can access the instruction memory. The ID stage, then the instructions are decoded, and then instructions access register file. Execution, the ALU is used and then to generate the result of instruction, the arithmetic or logic instructions. And the memory, then we can just access the data memory for load and store instructions. And then write back the result. The final result will be written back to the register file. So this is the write back stage. And then we learned that in the 5-stage pipeline architecture, then we can just split these steps, these 5 steps for executing instructions like this. So we can split. Then we can cut the critical path. The critical path in the processor design. So I mentioned that in a single cycle processor design, the critical path is like this one, right? So load instruction. But we can just cut this critical path like this. Then we can increase the clock frequency. Then how? How can we cut the clock? How can we cut the critical path? So I mentioned that this is the common digital design concept, right? It's the clock, and then this is the combinational logic, and then the delta t. So this is the delay of the combinational logic, and then I assume I mentioned that the TC clock period needs to be greater than this delay of the critical path. Then how can we cut the critical path? So you can find that you can find the deep flip-flop and then deep flip-flop here. So deep flip-flop is located at the start point of the combinational logic and then the end point of the combinational logic. And then this deep flip-flop provides the input data to the combinational logic, and then this deep flip-flop receives the result from the combinational logic. And then TC is to be greater than the delay. Now how can we split this critical path? We can just add another D flip-flop right here. So this is the clock signal. And then this combinational logic is split into the two parts. So combinational 1, combinational 2. And then this combination logic is connected to the deep flip-flop. So in this case, let us assume this is delta T1 and then delta T2. So TC, the clock period needs to be larger than the delta T1 and delta T2, right? Because you can just design this digital system like this, right? And then based on the timing constraint, then the TC needs to be delta T1 and delta T2. But we already know that we just cut this combination logic. So which means delta T1 is smaller than the delta T, the original critical path. Also, delta T2 is smaller than the delta T, right? So, but what can you observe? By adding and then by inserting deep flip-flop in the combinational logic components, then we can reduce the clock period, right? Because delta T1 is smaller than the delta T. We can apply the same approach for the pipelining design. Then how? So this is the single cycle processor. And then I mentioned that this is this yellow line. Yellow line is the critical path. And then we want to reduce the critical path of this design. Then we can just cut this combinational logic path, and we can insert what? D flip-flop. Okay, do you understand? So in order to implement, so you can just understand that this one. So in order to reduce the critical path, we can just cut the combinational logic path, and we can insert D flip-flop between this split the combinational logic part, and then it's the same. In the pipeline design, we can start from the single cycle processor architecture, and then, but in a single cycle process architecture, this yellow line is the critical path. So in order to reduce the critical path delay, then we can just cut this combinational logic part, and then we can insert D flip-flop. Okay, so, and then, the group of D flip-flops is called registers, right? So you can find so these D flip-flops, D flip-flops, D flip-flops, D flip-flops here. And then these D flip-flops are called the pipeline register. So this register is different from the register in instructions, right? So register in instruction is just the small memory for the instruction operands, right? But when we mention the pipeline register, then this register just represents the group of D flip-flops, okay? So, this is the D flip-flop. So actually, the clock signals are connected to this pipeline registers, okay? So, and then we can just call this pipeline register as the instruction fetch / ID. So it represents that this is the pipeline register located between instruction fetch and instruction decoding stage. Okay, and then so we can just use the same convention like the ID / EX. Okay, so this represents the pipeline register in the between the ID and EX stages. Okay, so if I use the pipeline register like this, then you can just figure out the location, the pipeline register in this pipeline architecture. Okay, so the first step is to just insert the D flip-flop in the critical path in the combinational logic part. Then, and then this is the first step. Then let's see how the instructions are executed in every cycle. So this is the example of load instruction. Okay, and then so the load instruction during the first cycle of the load instruction is fetched from the instruction memory, right? So this is the instruction, and then you can find that this is the PC, and then this is the PC plus 4, right? And then in the pipeline architecture design, you can observe that the instruction is given to the instruction fetch and ID pipeline register. So what does that mean? So I mentioned that this is the D flip-flop synchronized by clock signal. So on the rising edge of clock, this instruction and PC is sampled. Okay, so sampled, and then in the next clock during the ID stage, the sampled instruction and the PC value is given to the ID stage, like here. Then using this sampled instruction and PC value, then we can just access the register file. And then if we just access register file using the instruction field, then we can get register operands, right? And then we can also get the immediate value here. So, and then, this output of register file like RS1 data and then RS2 data and then immediate value. And then we already know that these operands will be used by ALU in the EX stage. So these output result of register file and immediate generator are also sampled by ID and EX pipeline register when on the rising edge of a clock. Okay, so it's sampled, and then the sampled value will be given to the ALU. And then for the load instruction, the ALU will calculate the address, okay, by using RS1 plus immediate. So this is offset. So this will be computed by ALU. Then also you can find that the result is given to the EX and memory pipeline register. So which means this result is also sampled by clock signal. So on the rising edge of clock, so this result will be sampled and then given to the memory. And then the result will be written back to the register file. But actually, you need to consider the timing. So what's the problem? So when the load word, let us assume that this is the load word X1. Okay, the destination register is X1. And then actually the final result of this X1 will be performed in the write back stage. Okay, so data is in the write back stage. But in this figure, you can find that write data is connected to this instruction. So what is this data? This is the output of instruction fetch and ID stage. So we can just represent this is as the instruction fetch slash ID dot instruction. What's the problem? This RD is the RD of ID stage. This data to be written back to the register file is the data in the write back stage. The problem is, data is stored to the register file, but this data is the data in write back, and then the RD is the RD in ID. What's the problem? Timing is different. This data, and actually in order to store data in the register file where we use the RD. So which means that the RD of this data needs to be RD in write back. So which means we need to check the timing of data in the pipelining register. So actually in the pipelining design, this is the tricky part. Okay. So Actually, this is not difficult. So based on this common design process of the design, we can just insert the D flip-flop in the combinational logic path, right? But actually, in order to support the correct operation in the pipeline design, we need to match the timing of signals. So like this. So if the data is in the write backstage, if we just store the data in write backstage, right? Then which means we need to use the RD in write backstage, not RD in ID stage. Do you understand? So this is very critical. So this is incorrect design. So actually, so as you can see, the RD, the write register is also sampled by this pipeline register, this pipeline register, this pipeline register. So you can find that this RD is the RD in EX stage, right? Because it's sampled by ID and EX pipeline register. And then this data is the RD in memory stage, right? And then if this RD in memory stage is sampled by memory and write back pipeline register, this RD is the RD in write back stage. So because this load instruction stores the data in write back stage to the register file, and then actually we also need to use the RD in write backstage, not RD in ID stage. So for the pipelining design, so firstly, we can just insert the pipeline registers, and then we need to match the timing of signals. So like this. So RD in write back and data in write back. Okay. So you need to understand that this, and this is actually some important part of the pipeline design. And then actually for the real design, actually some students can make mistake for this point. Okay. Okay. So I'll stop here. Is there any questions? Okay. So see you in the next week. okay. 감사합니다.